A point charge, Q1, which is 6e, is fixed at the origin of a rectangular coordinate system, and a second point charge, Q2, is negative 10e, is fixed at x equals 9.6 nanometers at y equals 0. Okay, so this is y equals 0, makes sense because it's on the y-axis. With voltage equals 0 infinity, the locus of all points also is v equals 0. Okay, so this tells us how we can define, this basically says that velocity equals kq over r, and the locus of all points xy plane, voltage equals 0 is a circle centered on the x-axis. Okay, yep, so it says that xc is on the x-axis. Find a, the location of xc, find r, the radius of the circle, and then is the voltage 5 volts equipotential also a circle, or is it a different shape? Okay, so what we're going to do is what I'm going to focus on here is just these points right here. That way we do linear, we don't have to worry about drawing triangles or anything like that and finding hypotenuse. So what I'm going to say, and this will be a bold statement, is that I'm going to call this point over here voltage left. I'm going to call this point over here voltage right. And I'm going to say that voltage left equals voltage right, which is 0. Right, so then I'm going to start by looking at voltage left. So I'm going to say that voltage left equals k q1 over r1 plus k q2 over r2. And all this means is that the voltage potential due to Q1 plus the voltage potential due to Q2 is going to equal our total voltage potential at left. And you might be thinking, well, the second one should be minus. It's going to be because Q2 is negative. So what we then get is something like K, and I think it's like, what is it, 6 and 10? Actually, I'm just going to solve it. So I'm going to say that K Q1 and then R1. So R1, and I'm just going to be concerned with magnitude here. So this distance right here is XC. This distance right here is going to be R. And this distance right here, I think they said 9.6. It's going to be 9.6. And I'm just going to leave it as 9.6. We know it's nanometers, but we'll deal with that later. And just for completeness, I'm going to say that this distance right here is going to be 9.6. Oh, this distance right there is going to be 9.6 minus xc minus r. So let's see. No, wait a sec. We got this. So that distance. Whoop. So this distance is going to be r minus xc. There we go. R minus xc, because this distance is r. This distance is r. R minus xc gives us that. And so then, also for completeness, this distance right here then is going to be 9.6 minus quantity r minus xc. And I know we'll cancel out the negatives. All right. So now that we've got all those distances down, for voltage on the left, that's going to be, the radius is going to be r plus xc. So we're going to do, oh, probably can't use black for that color. R plus xc. And then this is going to be minus equals 0. So what I'm going to do is I'm just going to flip Q2 over to the other side, switch the signs, and therefore kind of ignore it. So this distance is going to be 9.6 plus, just a sec real quick. No, I think I was wrong here. So this, let me check. So Q 2 point rectangular charge fixed at x equals 9.6. Okay, so some of this is going to be wrong, I think. So this distance right here is 9.6. This distance right here is xc. This distance right here is r. Therefore, this distance right here is going to be r minus xc. Yep. And so then this distance right here is going to be 9.6 minus r minus xc. Does that seem reasonable? That seems reasonable. 9.6. Yep. That might have been what we had before. Not entirely sure. Okay. Game face. So now this is going to be k Q2 over. Now the distance between Q2 and voltage L is going to be 9.6 plus xc plus r. Let's see, make sure I read that right. So Q1 is fixed at the origin, so 0, 0, yep. And then xc is to the left of that. Yep, okay. So I'll do 9.6 plus r, no, 9.6 plus xc plus r. There we go. There we go. All right, so now we're going to do some simplifying. K's cancel. So Q1 is 6 and Q2 is 10. So this is 6, this is 10, which I'm going to divide. I'm just going to divide both sides by 2. I'm going to call that 3. I'm going to call that 5. So this is going to be 3 times, I'm going to cross multiply here, 3 times 9.6 plus 3xc plus 3r equals, now I'm going to cross multiply this side over to there. We're going to have 5r plus 5xc. So then, let's see here. Simplifying this. 3 times 9.6 equals 2r plus 2xc. Okay, I'm good with that. And that is one equation. So now we're going to do the same thing with VR. So voltage on the right side of our circle. And that's going to be KQ1 over R1 plus KQ2 over R2. And I should probably put in some sort of subscript here to also denote that this is the radius for the right side from VR to R1, but we'll just kind of assume we know what we're doing here. I know. Big assumption. Big assumption. All right, so R1 is now going to be, so to voltage right, which is right there, that is going to be R minus XC. Okay. So I'm going to do R minus XC. I'll do a little imply sign. That way I don't have to maintain the whole equality here. I just flip it over to the other side. K over Q2. Now R2, this is going to be 9.6 minus R minus XC. So it's going to be 9.6 minus, let's see, did I say R minus XC? R minus XC. Minus R minus XC. Flipping this around, so the K's go away. Q1 becomes 3, Q2 becomes 5. So we have 3 times 9.6, we're going to cross multiply again, minus 3R plus 3xc. We've got the double negative here. 1 negative, 2 negatives. Equals 5r minus 5xc. Okay? And then working with this, we do 3 times 9.6 equals, let's see here, 5x, we have 8xc equals 8r. And this doesn't make any sense, so we're just going to turn that into a plus sign. Not that whenever something doesn't make sense, you just turn something into a plus sign. And this is going to be our second equation. So the easiest way to do this, I'm going to divide both sides by 4. So we're going to do 3/4 times 9.6 plus 2xc equals 2r. I just divided both sides by 4. So now you know what 2r is. So we're going to take our 2r up here, plug it in. So we do this, whoop, down like that. So now we're going to have 3 times 9.6 equals, now we know 2r is this, so it's going to be 3/4 times 9.6 plus 2xc plus 2xc. All right, so we're getting there, almost there. So now we can simplify this. So we're going to have, I'm going to change this 396 into 4/4. That gives us common denominator. So we're going to have 12 9.6s minus 3 9.6s, which is going to give us 9. 12 minus 3 is 9. 9/4 times 9.6 equals 4xc. We can solve this. So xc equals 9 times 9.6 over 4.4 squared, which is going to give us 16. Going over to Wolfram, I am going to do, let's see here, get rid of all this. We are going to calculate 9 times 9.6 over 16. And that gives us about 5.4. Okay. 5.4. So one thing to note, though, is that's a distance, not a position. So xc is actually going to be at negative 5.4 comma 0. So that gives us what xc is. Find location of xc, we did that. And the radius r of the circle. So now we want to find r, which shouldn't be too bad because we just solved what 2r is. So this is part A. This will be part B. So r equals 3 times 9.6 over 8, because I divided everything by 2, plus xc, which is 5.4. Putting that into a calculator, we get 3 times 9.6 divided by 8 plus 5.4. That gives us 9. Interesting. 3 times 9.6 divided by 8 plus 5.4 is 9. Okay, so the radius is 9. So then the third question, which gets a little bit tricky, I think, is equipotential equal to a circle. Okay, So I'm going to erase all of this. Actually, I'm just going to move it over here because I'm pretty sure I won't need it again. But just in case I do, I'll have it available. So we're going to go with the idea that voltage is going to equal voltage due to Q1 plus voltage due to Q2. And we're going to choose any point right here. And this distance right here is going to be X. This distance right here is going to be Y. So this is going to be K Q1 over X squared plus Y squared, square rooted, because it's the same as KQ over R. So KQ over R is voltage, and R is just going to be X squared plus Y squared, square rooted, plus KQ2, which will end up being a negative. Now, this distance right here is going to be 9.6 minus X. So this is going to be 9.6 minus X quantity squared, and then the Y is still going to be the Y distance square rooted. And so this is going to be K, which is just a constant. I think 8.99 times 10 to the negative 9 times 10 to the positive 9th, I think. And this will be 3 over X squared plus Y squared, square rooted, minus 5 over 9.6 minus X squared plus Y squared, also square rooted. Now, if I was a better person, I'd just look at this and rearrange it and be like, oh, this is a circle. I'm not that good of a person. So what I'm going to do instead is I'm going to go to Desmos. And Desmos, I'm just going to put in, let's see, 3 over X squared plus Y squared. Let's do X squared plus Y squared minus 9.6 minus X squared. So let's see here, that distance is 9.6 minus X, yep, plus Y squared. And we're going to set this equal to 5, because before it was equal to 0, because that's the whole idea with that circle. This is a 0 point. Now we're going to set it equal to 5. When I do that, I get something kind of like, interesting. Oh, pulling this over, make big. So yes, if we change the 5 to a 0, we get something that looks awfully like the circle we just had, centered at, looks like negative 5? Well, it was, XC was what, negative 5.4? Negative 5.4, so if we come back and look at this, it might actually be centered at negative 5.4. Yep, that seems reasonable. And then go 5. Not sure if that's a circle, but gee willikers, that looks pretty circular to me. So this isn't a math proof that it's a circle, but I'm going to say it's a circle. That's how to approach this problem. Hope it helped. See you next time.